Good evening, everyone. Actually, good afternoon for Professor Emilio. It's our really great honor and great pleasure today to invite Professor Emilio Martinez-Paneda to give a lecture in the College of Civil Engineering in Tongji University. So this is the number 106 lecture of the International Joint Research Center for Engineering Reliability and Stochastic Mechanics, and also the number 6T lecture in the Research Center for Engineering Mechanics. You may know that Professor Emilio Martinez-Paneda is a very famous researcher, especially in the field of computational mechanics. He is now associate professor at the University of Oxford. Prior to joining Oxford, he was a reader, that is associate professor at the Imperial College London, where he led an interdisciplinary research group from 2019 to 2023. Before that, he was 1851 research fellow at the University of Cambridge. His recent research focus has been on addressing fundamental scientific challenges that can accelerate our transition to a net zero carbon society and assist in tackling our energy and climate rises. Professor Emilio Martinez-Paneda has been the PI of quite a lot of projects, and his work has been recognized through many awards, including the 2021 United Kingdom Young Engineer of the Year by the Royal Academy of Engineering, and the 2022 Imperial College President's Medal for Excellence in Research, and the 2024 ICAM, the International Association for Computational Mechanics, John Agris Award. The title of his lecture today is Advanced Computational Methods for Predicting Fracture in Materials, Structures, and Ice Sheets. Now let's welcome Emilio to give the lecture. So Emilio, it's now your time.
Thank you so much for your very kind introduction, Professor Chen. I'm delighted to give this talk. Tongji University is, of course, very famous in civil engineering. We hold Tongji as the best university in China in civil engineering. So I always had a strong link with Tongji. I always wanted to get good students from there. You might actually notice that in some of the people that I acknowledge here, there is Chuanji Kui, who was a student in Tongji for his undergrad and master's. He did his PhD in Tongji, being a visitor with a CSE program at my university at Imperial, when I was at Imperial. And now he joined me at Oxford with a Marie Curie fellowship. So I always had very strong links with Tongji. We know that students at Tongji are excellent in civil engineering, and I look forward to continuing to collaborate with you. I visited Tongji, as some of you know, a year ago, and this year my travel was a bit more restricted, but I look forward to seeing you also in person in Shanghai. And this is the first of two lectures. I decided to focus the second lecture, which will happen in November, on more environmentally assisted cracking phenomena, such as hydrogen embrittlement and corrosion. But today I decided to focus more on the methodology itself, how we can predict fracture problems. And I'll showcase examples across multiple areas within civil engineering. But before I do so, let me just say a few words about myself. I have the pleasure to meeting many of you, but not all. So just a reminder, as you can probably guess from my complicated name, you see I have an accent here, as a weird symbol on top of the N. That means that I'm from Spain. This is where we use these funny characters. So I was born and raised in Oviedo, which is a city in the north of Spain. You can see it here. This is the map of Europe, and this red area here is the region where I'm from. The region is called Asturias. And it's a very beautiful region. You can see here some pictures. So if you have the chance to travel, I'll recommend coming along. You see we have nice beaches, mountains, cows, cathedrals. So it's a very beautiful area of Spain, but it has been a long time since I don't live there. I did my undergrad in my home university, the University of Oviedo. This is very typical in Spain. We normally stay around. live with our parents for our university degree. Then my academic career, my PhD, took me mostly to Denmark, also other places like Luxembourg or the University of California, Santa Barbara, but mostly to DTU in Denmark, somewhere here. And then I stayed a little bit as part of my PhD as well at the University of Cambridge with Professor Norman Flack. And I continued in Cambridge later on, first as a postdoc and then as an 1851 research fellow, before taking my first academic position as a lecturer, assistant professor at Imperial College London. And some years ago, I moved here to Oxford. And I'm very happy to be at Oxford. Oxford is a very unique place in many ways. It's not only the oldest university in the English-speaking world, or almost 100 years old, as you can see there, but also it is a very nice place to be because it's a very international environment with very brilliant minds from all over the world. So it's a very exciting place to be, and there's a lot of great ideas, seminars, Harry Potter dinners, as you can see here. So there's a lot of things that are going on there. And of course, you're all welcome to visit Oxford. If any of you happen to be in the UK and want to come through Oxford, please send me an email. I'll be very happy to take you to one of those Harry Potter dinners if you're interested in. Anyway, it's a great place, and I'm very lucky to be at Oxford. And at Oxford, I established my group, which is called the Mechanics of Materials Lab. It's a relatively large group. We are now 21 people between postdocs and PhD students. There's people from all over the world. You can see some of them here. Tongji is here. We also have, of course, other people from China. You see Runzi, Yang, and a few others. But it's a very international group, and we have people from all over the world. And these are basically the people doing the hard work, the PhD students and postdocs really carrying the flag of the group. And what we work is in a variety of topics at the interface between civil engineering and other disciplines. We search for interdisciplinary problems. Those are typically the most exciting ones, the richer ones, the more challenging ones as well, and typically related to applications related to the energy transition as well. Not only, but related to the energy transition. So you'll see, this is our logo. We have hydrogen applications, energy like batteries, offshore wind energy, glaciology as well, ice sheets, sustainable structural materials, and a few other items. But basically, what we do is a combination of experiments and modeling to try to understand some of these problems. And I would say one joint feature to all of these efforts is structural integrity. We care about the integrity of the structures. We try to predict when things fail. And of course, this is what some people call the discipline of fracture mechanics. And the discipline of fracture mechanics kind of underpins a lot of what we do. So this is why today I wanted to talk to you about fracture mechanics and about what new computational tools are coming along to predict fracture phenomena. And you may wonder, okay, fracture mechanics have been there for quite a long time. Engineers use fracture mechanics all the time. Why is there such a big research interest all around the world on fracture mechanics? And for that, I'd like to quote Bazin, who's a professor at Northwestern University and considered to be a giant in mechanics and in civil engineering. You probably all heard about him giving his work in concrete materials and other areas. And Bazin said that, many hot research subjects become closed in a few decades. But like turbulence, fracture mechanics is different. This formidable subject has been researched for over a century and probably will be for another century. So this is quite interesting and true, of course. Fracture mechanics continues to attract an ever-increasing attention. And one wonders, why is this the case? Why do we care so much about fracture mechanics? Why it has been there for such a long time? Of course, part of the answer to this is related to its importance, right? Fracture mechanics underpins a lot of phenomena in nature and technology. I just put some examples here. In order to predict sea level rise, we need to understand how glaciers fracture. I'll discuss this later on. Energy infrastructure for hydrogen, for batteries is critical, relies on cracking phenomena. This is what compromises the energy transition. You see here cracks in lithium-ion batteries. This is wells for hydrogen transport. And of course, also transport, we know. Most of the times when we see a problem with a train, we know that it's related to fatigue cracks that have originated there. So of course, it's critical to many areas of science and engineering. That is a problem. So that's one of the reasons why it's of interest. But of course, you could argue, well, maybe through the years, we have learned enough that it's a problem for engineers, but not for scientists. But it's a problem for both scientists and engineers because it's a challenging problem. And it's a challenging problem from both mathematical and physical perspectives. From a mathematics perspective, we normally don't like cracks, right? We like things that are smooth. So we like smooth displacement fields. But the moment we bring a crack, we bring a discontinuity. And then you need to track a discontinuity, you need to track an interface, and you need to see how this thing evolves. So that's a challenge, a long-standing challenge, I would say, from a computational mathematics perspective. The other issue is the physical challenges, right? So trying to predict fractures. Fractures sometimes are relatively easier to understand. If we think of materials in isolation, we think of stress intensity factors, toughness. These are well-established concepts that are part of engineering standards, but often they're very difficult to understand as well, because often we have failures in the presence of an aggressive environment. It could be a corrosive environment. It could be an environment containing hydrogen. Often it's a multi-scale process. So not only the fracture resistance of materials and structures is very sensitive to the environment, it can also be very dependent on a multi-scale phenomenon. It could be due to things that are happening at atomic scale, at the dislocation level, at the continuum level. So we need to be able to understand the material physics underpinning fracture. And I think this is one of the reasons, or the main reason, why we are so interested in fracture through many years. However, the point that I will try to make today in my talk is that part of the challenge has been solved. Recently, thanks to exciting developments in computational fracture mechanics, we are now being able to handle this part of the problem. We still have a lot of questions about the physics and how cracks develop in very different interdisciplinary multi-physics environments, but we now have robust tools that allow us to simulate how cracks evolve. And the main methodology that I want to discuss today is called the facial fracture method. And you can see here in this summary slide some of the results that you can obtain with these new technologies. And here and throughout my presentation, every time I show red color, this means a crack, so all of these are cracks, and blue color means intact material. And these are a summary of results from my group, but also from other groups in China, in the US, and in Europe, and elsewhere, across very different materials, so metals, ceramics, rocks, composite materials, functionally grid materials. And you can see that the method is compared to experiments, and the method not only seems to be able to capture very complex cracking phenomena, but is able to do so showing a remarkable agreement with experiments. You can see here, these are nuclear ceramics. You can see very complex cracking phenomena, and the method nicely captured this. This is a mode 3 type of propagation, thermal shock, multiple cracks getting very similar spacing and crack length, and so on and so forth. So this is quite exciting. And this is a field that has gained significant attention in everywhere, of course, also in China, where many important developments are arising. And one way of showing this, I recently gave a talk to a conference in this area, and I summarized. I went to Google Scholar, basically. I searched for how many papers included phase field, the keywords phase field and fracture. And you can see that the number of papers has been growing almost exponentially. And we are now above 5,000 papers per year. This is roughly a third of fracture mechanics papers and the vast majority of computational fracture mechanics paper. So the method has really taken the community by storm. We are really seeing significant attention. And there's a lot of people interested in adopting this method and applying this method to different problems. Basically, I started in 2010. This is when Christian Mier started making some contributions that make the solution of this problem much easier. And as you can see, the trend is really growing and growing and growing. And it's becoming by far the most dominant technique in computational fracture mechanics. So why is this? What is all this method about? So the idea is relatively simple. Whenever you have two faces, you can think of a blue and a red face. You can think, for example, of a blue being the uncracked material and red the crack. So you can think of this interface as sharp and discontinuous, and this is what we discussed before. It's a mathematical problem, a mathematical challenge. Or you could smear the interface over a finite domain using an auxiliary variable, the phase field, to tell you where the interface lies. So the phase field will take a distinct value in each of the phases. It will be 0 in the blue phase, 1 in the red phase, and then it will vary smoothly in between. And then what you need to do is you just need to define a differential equation for the evolution of this phasal variable. And by doing that, you're able to predict interfacial problems of arbitrary complexity. So it's an implicit representation of interfaces that overcomes all those challenges, mathematical and computational, that I mentioned before. So for example, some of the key advantages is that you define the interface equation in the entire domain. So you don't need any moving boundary conditions. You don't need any special treatment for the interface. Another advantage is that topological changes, such as, for example, branching of cracks, coalescence of multiple cracks, they are all naturally captured. You don't need to add any criteria. It comes naturally as an outcome of the simulations. And importantly as well, for many of the interesting problems that we're looking at, is very well suited for multiphysics problems, because you can easily combine the interface equation with other equations describing other physical phenomena. And phase field modeling has been used beyond fractal mechanics. It has revolutionized many applications in science and engineering. It all started in the condensed matter physics community, where it's now by far the most widely used technique to simulate microstructural evolution. My focus today is on fractal mechanics, but we have also shown, my group, but also a group in the US and a group in Hong Kong, that it can be, the same paradigm can be used to predict corrosion. And I will discuss this on my lecture in November. You can see how you can use the phase field to describe the evolution of a corrosion front, material dissolution, the interface between the metal in red and the blue, the seawater, the electrolyte, whatever electrolyte you have. So this is another area that I think is quite exciting, and a newer application of phase field, what I think is going to be a revolution as well, because predicting corrosion with computers is a complicated task. But anyway, my focus today is on fracture mechanics. And again, this is the output of a simulation. This you can see is hydraulic fracture problem. You can see very complicated cracking patterns, crack branching, coalescence of multiple cracks, nucleation of secondary cracks. Predicting this kind of phenomena with other methods was very difficult, if not impossible. So phase field has really opened new horizons. But this is only one part of the reason, or one element of its success. There's two aspects that I think are critical to, or three aspects that I think are critical to its success. One is that allows us to calculate very complex cracking phenomena. The other one is that it's physically sound. We need to make sure that, of course, the nice colors that we're getting in our computer correspond to physical reality. And the last one that I'll also discuss later is that it's mathematically or computationally very robust. We don't get convergence issues and so on. But let me focus first on the physical aspects now. Okay, so it's clear we get nice colors. Are those nice colors sensible? And I think one of the beauties of this phase field method is that they provide a platform, a computational platform for Griffith's energy balance. So those of you familiar with fracture mechanics, you will remember that, Griffith is the father of the discipline. He said, in order to be in agreement with thermodynamics, for a crack to grow, the energy stored in the solid has to be equal or larger than the energy required to create tuner surfaces, basically. What we call typically GC, the critical energy release rate, or the fracture energy, or the toughness. And you can express this kind of energy balance, thermodynamic energy balance, in a variational form. And if you do so, and you're able to minimize this functional, then you can naturally predict how cracks evolve as an exchange between stored energy, the energy that is stored in the material, that depends on the mechanical strains, and fracture energy, the energy required to close cracks, basically. But minimizing this functional is complicated, because you don't know where your crack lies. You have this surface gamma, this integral gamma, and you don't know where your crack lies. So what you can do is to use the phase field paradigm. So the phase field, this auxiliary variable, goes from 0 in intact material points to 1 in fully cracked material points, and then varies smoothly in between. So it's a little bit like a damage variable. It goes from 0 in points that is not damaged, 1 in fully damaged points. And like a damage variable, of course, it reduces the load carrying capacity. This is the strain energy density that, of course, depends on the strains. And then it's a little bit like a non-local continuum damage mechanics model, in that you have a gradient of the phase field, which naturally brings a length scale, and I'll discuss this length scale later on. But what this means from a computational perspective is that if your mesh is fun enough to resolve this length scale, your results are mesh independent. Your results are mesh objective. So that is one of the beauties of the method as well. But basically what the phase field allows is to regularize this functional. You go from a surface integral to a volume integral, and it's very easy to solve this problem now using the standard finite element methods. And you can get a good overview of the method by just looking at the strong form of the balance equation. So you have the usual balance of linear momentum that you solve in any standard finite element simulation, where the phase field is degrading the load carrying capacity of your material. So whenever the phase field is equal to 1, you have a crack, no material to carry any load. And then the other situation that you have is a differential equation for the evolution of the phase field, which is effectively a competition between the strain energy density that increases with mechanical strains, the energy stored in the material, and the material toughness, GC, which is something that we can measure through a fracture toughness experiment. And just by solving this differential equation, we're able to capture fracture problems of arbitrary complexity. You can see here, for example, crack branching due to the application of a dynamic load. So here you see, because of the wave interaction, you see that the cracks are branching. And this I can capture on my original finite element mesh and without any convergence problems. So again, the reason why the method is so popular is because it's computationally robust. We can predict complex things without convergence issues. As you can imagine, fracture mechanics is challenging from a convergence perspective. You go from something that is carrying load to something that fails catastrophically where the carrying capacity is lost. And it's also a method that is physically sound. It's all based on thermodynamics of fracture, the balance of storing energy versus releasing energy to propagate a crack. And the beauty of being based on the thermodynamics of fracture and this framework that Griffith and then Orawan established is that it's in well agreement with fracture mechanics theory. I will discuss that in a minute, but this is quite important because when we work with industry, they know that they can use this method. They know the inputs to this method is values that they know. You know, they work themselves with fracture toughness, so they know what is the fracture toughness of their material. And they know that the method is going to give them the same answers as the simple engineering standards that they're using for the simple cases where engineering standards apply. But then they can use this method that seems consistent with everything they know for more complicated problems. But let me tell you a little bit about these two aspects. Okay, why is it computationally robust and why is it physically sound? So let's look at the numerical implementation first. So those were the strong form equations that I told you before. And of course, if you want to postulate the weak form, then basically you have this for the mechanical problem and this equation for the phase field problem. And you can see that you're basically solving this kind of coupled problem where you solve for the displacements and the phase field. You define this stiffness matrix that is the same as usual, just with the phase field degrading the material capacity. And then you have a phase field, you have the residuals, of course, for the displacement and a residual for the phase field and the stiffness matrix for the phase field. So it's very, very easy. I mean, the phase field is a scalar. So those of you that like to play with your own finite element code, implementing this will be very straightforward. We have released openly all our codes, and we have implemented phase field in many different platforms. We have implemented into Abacus, for example, using very simple user material subroutines that take advantage of the analogy of the phase field equation with the heat transfer equation. COMSOL now has phase field as an inbuilt feature. So if you download the standard version of COMSOL, you just click a button and phase field fracture shows up. So it's already an inbuilt feature of some commercial finite element packages. But again, very easy to implement in many ways. We have released MATLAB code, C++, Phoenix, Julia implementations, and so on. But if you work with your own finite element code, it is very, very easy. You just need to add this coupling term here, add this coupling term, and then define this residual, one line of code for the residual, one line of code for the stiffness matrix. Very, very easy. But when it comes to solving it, one wonders, okay, why is this method more robust than other computational fracture mechanics methods? And this is a little bit related to the way we solve the system. The flexibility that you gain by solving for the damage variable independently, so to say. Because of course you can see that, you know, if we're solving the system of two unknowns, the displacement and the phase field, there's basically two ways that we can solve the system. One is through what we call a monolithic approach. So we solve at the same time for the displacement field and for the phase field. And this is good because it's unconditionally stable. So you can run implicit simulations with very large time increments. The problem is that this regularized functional is non-convex with respect to the displacement field and the phase field. So convergence can be a bit tricky. And this is the usual problem for all kind of non-local continuum damage mechanics models. So what a lot of the community is doing what they call a staggered approach, where they first solve for the displacement, and then with the displacement field, they freeze, they solve for the frozen, they solve for the phase field. So you solve one and then the other, basically. You solve them sequentially. This is also called segregated or staggered approach. And this is very good news because for a fixed displacement, the regularized functional is convex with respect to the phase field and vice versa. So convergence is very, very good. It's very, very powerful. However, when you're using a single pass approach, for example, you're going to lose that unconditional stability. So it becomes sort of like a semi-implicit method. You really need to use small increments. So the approach that we have championed, and also others, in particular Wu's group here in China, is to use a monolithic and quasi-Newton approach. For example, methods like the BFGS, because that gives you the robustness of the staggered approach with the ability of having an unconditionally stable method as the monolithic approaches do. So it's the best of both worlds, basically. So I'll show you in a minute how it works. So this is a classic benchmark example. So you have a plate. This is a classic benchmark in the phase field community. You have a plate, square plate, with a crack subjected to uniaxial tension. The material is linear elastic, so mode 1 fracture, you apply a load, the crack is going to grow in an unstable fashion. You pull, and the crack will go immediately in one step across the entire plate because it's a linear elastic material. It's mode 1 fracture, it will just grow unstable. So this is what you see here on the right. Look first at the red curve. This is the force versus displacement curve. You can see that initially everything is linear, then eventually a little bit of nonlinearity due to the damage, and at some point, this unstable crack growth event happens, and you lose all the load carrying capacity, and you end up here. And you can imagine how challenging it is from a computational perspective when you use a Newton method to jump from here to here, right? You need to find a way of you're looking for a solution somewhere near here, but your real solution is actually down there because your crack propagated suddenly and you lost all your load carrying capacity. But you can see that the phase field is able to actually predict not only the unstable crack growth, but even what happens after that crack has fully propagated. So it's very robust. And what you see here on the left, each of these bars is a load increment. I took 30 load increments. I could have taken 12, but I wanted to resolve more nicely this part here. So I took 30 load increments, and each of these is the number of iterations. And you can see that initially convergence is pretty fast. And then funnily enough, when you are in this very critical load step, you need 200 iterations, which is quite a lot. Normally, you don't expect Newton methods to converge after 5 iterations. But here we converge after 200 iterations. So it's something, I would say, relatively unique to the phase field in the sense that by isolating the phase field, the damage variable, from the displacement field, you gain this additional robustness. I mean, even thought you need 200 iterations here, the total number of increments and iterations is very small. So I can run this simulation that is an unstable fracture event in my laptop in, I would say, seconds, maybe a few minutes, let's say 1-2 minutes. So it's very, very fast, and this is the beauty of it. And the beauty of this quasi-Newton method is that when you compare to the single pass stagger approaches, you can see that in order to reproduce the right force displacement response, the stagger approaches, you need to use many increments because you have some sort of semi-implicit method, but you can capture the right result with very few increments with this monolithic approach. And when you compare the total number of iterations, you see that you can reduce the total number of iterations by orders of magnitude. So this BFGS quasi-Newton approach, I think, is quite powerful. So this is one aspect of it. Why is it computational robust? Well, because you're solving these two problems independently, the functional becomes convex, but also because we're developing techniques like this BFGS and quasi-Newton approach that make it very powerful. So that takes me to the other aspect of it. Okay, why is it physically sound? Well, because it's based on fracture mechanics and the thermodynamics of fracture, so it predicts failures based on input parameters that we fully know. So basically, the input parameter you need is the fracture toughness, the GC, and you can show it mathematically using gamma convergence, but you can also use computationally that indeed this is the case. You predict the fracture would initiate when your energy release rate reaches a critical value, or your stress intensity factor reaches the fracture toughness, a critical value. And you can see this here, G versus GC at the initiation of crack growth versus the length scale divided by the element size. And you can see that if you have a very coarse mesh, then you get a bad result. But as you refine your mesh, eventually you get a converged result, something that converges towards 1. So you do get the fracture initiates at the right time if your mesh is fine enough. You can see you need 6-7 elements to discretize that interface. And then you have this subcritical crack growth. We also check that this is correct not only to the initiating a crack, but also to propagating a crack. So you can go here, we applied a remote K field or J field using the Williams expansion. Here we use a double cantilever beam. So it's a problem where we have an analytical solution using Timoshenko's beam theory to predict what is the energy release rate. So we can plot crack extension versus applied displacement. And we can see that again, we're in good agreement. And that is one key element here. So that is good news. At this point, you may wonder, okay, Emilio, you're right. The model has only 2 parameters, this GC and this length scale. the GC is clear. The toughness has a clear physical parameter. We know how to measure in the lab. We use it all the time in engineering practice. What about the length scale? Well, the beauty of it is that through the incorporation of this length scale, you bring the concept of strength into the model, which is something that is absent in Griffith's fracture theory, but is physical. And you can see this here. So if you take a 1D example, so you take an homogeneous problem where you forget about the gradients, you can do that analytically, or you could just take a one element problem in Abacus or in your favorite finite element code and load it. You see that you get this sort of a stress strain displacement curve that resembles very much the kind of traction separation displacement curve that you'll see when you use Quiz-Zone elements. So you see that you increase, and at some point you reach a strength after which you start dropping your load carrying capacity. And analytically, you can find that for the standard 82 phase field model, there is this relationship between the strength, the toughness, Young's modulus, and the length scale. So the length scale has a physical meaning. It basically tells you a little bit, it's an indication, it's proportional to the fracture process zone of the material, which makes sense, of course. Every time we talk about a fracture toughness, we have a naturally, bidimensional consistency, we bring in a fracture process zone idea. So we need to be able to resolve the fracture process zone, and that will be, of course, a material property. Different materials have different sizes of fracture process zone. So basically, by picking your length scale, you are picking the strength of your material. So this means that the two parameters that we need are either the toughness and the strength, or toughness and length scale. They are the same. We have three parameters here. So we basically, everything relies on two parameters that we know very well, the strength and the toughness. And this is very nice because it allows us to capture not only situations what we call toughness-dominated fractures, but also strength-dominated fractures. And you may have seen this before. So if you take a fracture mechanics course, they often talk about the transition flow size. This is something that, for example, the nuclear energy uses all the time. So this is crack size on the x-axis, failure stress on the y-axis. If your crack size is big enough, then you know that fracture mechanics applied. The crack will grow based on this Griffith's energy balance, on the stress intensity factor. If your crack is very small, then you get yielding or you get strength-driven failures before fracture. So you have this transition from this type of failure to this fracture mechanics type of failure, and then industry uses one or the other depending on the size of the crack or their inspections. But what you can see here is that the phase field model is able, the symbols are the phase field calculations. We basically took a plate with a crack and changed the crack size and calculated the failure stress. And you can see that the phase field is naturally able to go from this fracture toughness domain to this strength dominated domain. And this is good news because it means that it doesn't matter what is the size of your crack, the phase field is going to give you a result that is physically consistent. And this is, of course, what we see also in experiments. These are experiments of fracture stress versus crack length on various materials. And you can see, of course, that we see exactly the same trend, and that therefore the phase field can handle any arbitrary length scales. And at this point, I'll say a few words about nucleation of cracks in phase field, because this is still an open issue in a way. There's still very much a lot of people working on this as we speak. And the reason why we're still a lot of people working on this is that you can show very nicely, and there's this nice paper by Tanea et al., using, for example, notch samples. These are notch samples where they change the notch radius and they compare two experiments on a wide range of materials. So you can show very nicely that the phase field indeed captures the right nucleation strength, is able to calculate very nicely when cracks nucleate, and is able to do so, showing a good agreement with experiments. But of course, sometimes, and this is particularly relevant to civil engineers, you're working with materials where cracks nucleate under compression, macroscopic compression. Of course, locally it's always tension, but macroscopic compression. So you need to be able to include arbitrary failure surface. And this is what you see here. So this is the principal stress space. And you can see that the yellow line is basically what you get with the standard phase field, because the standard phase field is all about energy, right? And the energy doesn't know if you're talking about compressive stresses or tensile stresses. You just have an energy, strain energy density. So the standard phase field works very nicely when you're talking about fractures driven in this domain by tensile fractures, which is typically what we're interested in. For example, in metals, we don't see failure in the compression. However, you could say you could have other situations. You can see graphite here. This is the case of graphite, where fractures not only occur under tension, but also under other situations. So the ability to enrich phase field models with an arbitrary failure surface would allow you to predict at the macroscopic scale when you get failures under compression behavior. So there's a lot of people who have come up with ways of doing this. Sometimes they call strain energy splits. So what they do is, instead of taking the full strain energy density as the driving force for fracture, so all the energy stored, they divide that into an active part and an inactive part, or sometimes called a tensile part and a compressive part, and then they drive the fracture only through the active part. And this is what you see here with the volumetric, the bitoric. This is the failure surface that you get. With the no tension split, that is quite used for masonry materials, you get something like this, and also the spectral split. But there are many others, and there's a lot of people working on trying to incorporate any arbitrary failure surface. So you say, now I'm working with granite, with cast iron, with this type of rock. Okay, we have these experimental data points. Let's feed that to a failure locus and bring that failure locus into phase field. So this is a very much an ongoing area of work. And just to cite a few people, the group of Laura De Laurentiis at ETH, they're working on their star convex model. We have proposed a generalized energy decomposition that allows us to implement easily things like Drucker-Prager. There are also non-energetic models by the group of Oscar Pamies, John Dolbo, and Luc Kumar, and also the group in France, they have also a special formulation where you have an eta parameter that you can calibrate as well to kind of capture this. So this is a very much an active area of research when we're looking at fracture occurring in compressive areas, basically. Another active area of research is fatigue. So this is basically the function that I will show you later. So a lot of people said, okay, we care about cyclic loading. This is, of course, of interest to civil engineers. So we now try to see, can we extend this framework to account for fatigue? And there's various approaches out there. The one that I like the most is the one by Laura De Laurentiis' group, where basically they say, okay, what we can do is we can add a fatigue degradation function that basically degrades the toughness. So this fatigue degradation function will accumulate, will evolve with accumulated load. As you increase your load, as you accumulate cyclic loading, you will increase that number, and therefore you will degrade this fracture energy. And that basically means that you need to come up with, well, what drives this alpha parameter? What is the variable that is accumulating? Well, that's simple. We keep it energetic. It's driven by the strain energy density. And also you need an extra parameter. You need, well, two part things. You need a degradation law, how a material will degrade for a given cyclic loading history. And that, of course, is material dependent. So you need some calibration with experiments. And in their simplest version, they had a model that relied purely on one calibration parameter. And they showed very nicely that once you calibrate the parameter, you're able to capture both SN curves and Paris law behavior as an output of the simulations. We're not inputting the Paris law parameters into the model. We are running, you see, a compact tension sample for different loads, and we are seeing how the model captures the stage 1, the stage 2 Paris law, and also the complete failure. And the same goes for SN curves. So things come as an output of the model, as a natural output of the model, not as an input. And I think this is very powerful because then we can handle arbitrary loading conditions. One thing we did work in my group is that we realized that this model of Laura was very good. It was a very nice framework, but we weren't able to get quantitative agreement with experiments. So we extended the model to account for an extra parameter. And I don't have time to get into the details, but the paper's out there for anyone who's interested. But we extended the model for account to this extra parameter. And so the price to pay was to add an extra parameter. But the advantage is that we were able to predict quantitatively what we see in the experiments. So you can see, for example, here, that once we know the value of these two material parameters for this particular material that we're interested in, we can then simulate fracture experiment or fatigue experiment, these are SN curves, at different load ratios. And you can see that we can naturally go from one to the other. So you need one experiment of your relevant material, and then we can predict what's going to happen in the lab, but also in engineering practice and the different loading conditions. So I think that is quite powerful. And the other advantage, of course, is that you can handle any arbitrary geometry. So here is the SN curve for a sample that is unnotched. There's no crack in there. But then you could add defects of various stress concentrators, and you can see that the model is able to capture this. And this is also of interest for those of you working on computational mechanics, because the beauty of these models is that you're simulating fatigue processes as they happen in reality. So you don't need to make any strong assumptions. You can capture any geometry, any loading history. So, overloads, you can capture anything that you're interested in. But the price to pay is that, of course, these are heavy calculations because you're running things cycle by cycle. And a lot of engineering components fail after millions of cycles. So we need to be able to run millions of cycles in 2D, in 3D, in our computers. And we need to be able to do that fast for industry to be interested in this. So there's a lot of interest from the computational mechanics perspective, trying to accelerate those calculations. There's many groups working on this, again, all around the world. Of course, we are trying to contribute to this. So I'll only talk about my contributions due to the lack of time, but many interesting things are coming out these days from various groups around the world. What we try to contribute is, for example, using those BFGS quasi-Newton approaches. And we have shown that in a very first paper. We did fatigue, and we showed that with a monolithic quasi-Newton approach, we can solve the problem with 4 increments per cycle. You can also do that with a single pass scheme, but you need to use a lot of increments per cycle, not even with 500 to get the right result. So it becomes prohibitively expensive to run fatigue simulations with single pass standard schemes. We've also proposed a constant load accumulation scheme that is based on the idea that often damage only accumulates during the tensile cycle, so you can jump across these tensile cycles. And we have also combined this with another idea that a lot of people are exploiting that is called the cycle jump. Basically, this idea means that if you are running a simulation to predict a railway component that is going to fail after 30 million cycles, maybe cycle number 26 is not that different from cycle number 27. So instead of simulating every one of those 30 million cycles, maybe you can simulate 1 cycle every 10 and assume that the other 9 are going to be very similar. So this is something that we have also explored, and we also explore these modified Newton schemes because maybe you don't need to update your Newton or your stiffness matrix on every increment. You can assume that it's going to be similar over some of those cycles. But what I want to say is that the point that we are at the moment, this is with our Julia implementation, is that we can run 3D simulations over now millions of cycles. This is an example from some years ago. You can see here, this is a 3D component where it has a notch or a crack that has a funny shape, it's tilted, which will lead to some sort of mixed mode cracking. You can see that the cracking is unconventional. And because the cracking is unconventional and we want to capture, we have a very fine mesh with 3 million degrees of freedom all around the potential energy of area of growth of the crack. And we're solving, you see here, 600,000 cycles. Now we can do millions. And this is, by the way, using a direct solver and doing 1 every 4 cycles. So we could be much more aggressive in the cycle jump scheme. So I think what I want to show you here, or the takeaway, is that we're reaching a point where computers are big enough, and we have good enough ideas from the computational mechanics side of things that we can predict large fracture process in 3D with millions of degrees of freedom over millions of cycles. So this becomes very relevant to engineering practice. And then I'm approaching the second half or the end of my talk, so I just want to finish with some examples of various applications where we have shown or we have tried to contribute to the face field fracture community in our group by developing new schemes across various applications that I think will be of interest to you, civil engineers, so including rocks, ice sheet fracture, smart materials, batteries, functional grade materials, and concrete. I'll discuss corrosion and hydrogen embrittlement in the next talk in November. So let me start with rocks. And let me start by showing what I think is a very interesting example. So this is what they call a blind or round robin test, where basically it was called the damage mechanics challenge. It was organized by Sandia National Labs in the US and Purdue University. And they basically made a call to everyone working on damage mechanics or fracture mechanics around the world. And they said, we're going to 3D print a rock. We're not going to tell you what material we're working on. And it's a 3D printed rock, so it's going to be difficult for you to find data on this. It's very unique material. So we're going to 3D print some sort of material. I think it's similar to gypsum. But anyway, they didn't give us that information. They said, we're just going to 3D print a rock. We're going to 3D print multiple samples. As you can see here, they printed a lot of samples. Some will be conventional. We'll test all of those samples, and we'll give you the result of some of the tests. But then we will ask you to blindly, without seeing the outcome of the experiments, predict with your computational models what is going to be the output of those experiments. And then you send us over to us your simulation results. And once we have the simulation results from everyone, we will release the output of the experiments. So I like it very much, actually, because when you, as an academic, when you publish a paper and you show a nice agreement with experiments, well, you never know how much of fitting was involved in there, right? You know what the right solution has to be, so you can iterate. There's some room for iteration and calibration. But here, this is much more risky because they are telling you, okay, you need to send us your calculations and we're going to publish those calculations. So if your method is not very good, everyone is going to be able to see that your method was not very good. So this is what I find quite interesting. And basically the data they gave us was a uniaxial compression test, which allowed you to estimate the compressive strength, a Brazilian test, which if done properly allows you to estimate the tensile strength, and then a 3-point bending test, which would allow you to estimate your toughness. So again, this is enough for us because then we are able to get the inputs of our model, which are strength and toughness. And this is the advantage versus other models that rely on many parameters that we don't know very well what are the physical meaning. So I'm not surprised that models that have a lot of parameters are able to fit experiments because, you know, if you see an experiment and you can calibrate many parameters, that's not a surprise. But the ability to blindly predict experiments with as little parameters as possible, this is what I think makes phase field very powerful. And so then basically they said, okay, now we want you to tell us the output of 4-pole bending tests that are basically unconventional notch configurations. And they have DIC data and they have force displacement curve data that they didn't give us, and also XCT data. So we did that. We said, okay, they give us the geometry of their experiment. So we went with our model and we said, okay, we predict, you can see here they have different 3-point bending configurations where they have a 4-point bending, was it? Yeah, 3-point bending, sorry. 3-point bending configuration where they have notches in different locations. So you get kind of mixed mode cracking. And then we didn't know what the experiments look like, but we run our simulations. We predict these crack trajectories on the left, and we predict these force displacement curves. We send it over to them, and then when they have the results from everyone, they release the data. And this is how the data look like. First, in terms of force displacement, they did 3 replicate experiments, and you can see we got a very good agreement all across the board. There's a little differences here and there, but more or less they are within the experimental scatter. So we were quite happy with the outcome. Again, this is a blind prediction. We did not see anything of the experiments. Then they also released the crack trajectories. And again, as you can see, the experimental crack trajectories are very well aligned with ours. In fact, we can overimpose them. And you can see the agreement is almost perfect. So we were quite happy. I mean, it's not that difficult to get these things when you are allowed to recalibrate your model. But if you do it blindly, this is quite nice, I think. And then finally, they did one case in the XCT scan. So they have a full 3D representation of your crack morphology. And they said, okay, those of you that are brave enough, do a 3D calculation and tell us what crack morphology you get. So this is what we did. This is the calculation of 3-point bending. The crack is tilted. You can see how the crack grows, the whole crack surface going all the way through. And then we compare that with the XCT image that they obtained, that they compare with the XCT image that they had, and the agreement was very good. You can see this here a bit better. So this is the XCT image that they got of the crack surface. This is the MATLAB reconstruction of the XCT image, and this is our prediction. Again, a blind prediction, 3D crack surface. You can see that the agreement, I think, is quite remarkable. So this is the first part when it comes to rocks. So we have a model that we believe can blindly and nicely predict rock experiments. And what we're interested in is in extending this to hydraulic fracture, where you have not only the fracture of rocks, but also an interaction with other disciplines or problems, so to say. This becomes a multidisciplinary problem because you have fluid flow and some pore mechanics. But again, we exploit this ability of phase field methods to combine the phase field equation with equations describing other physical phenomena. This is a phase field hydraulic fracture model that we just released in CMME. And we've released the code, so you can easily implement this into Abacus. But the idea is basically that in addition to the phase field, you solve a pore mechanics problem, and you solve an equation for fluid flow using Darcy's law, where you basically interpolate using the phase field between the reservoir, transient, and fracture domains. You interpolate the relevant properties, and then you can predict anything you want. These are some classic benchmarks. You see here how, let me run it again. You inject a fluid inside of a crack, that crack grows, links to the other crack. This is the pressure fields. You can see how they evolve inside of the fluid. So both 2D and 3D, we have done this in 3D as well. You can calculate easily what is the propagation of cracks and the interaction with fluid injections. This is another classic example where you have another crack that is starting to grow and then eventually interacts with another crack. Then the fluid propagates in there. These are classic benchmarks in the hydraulic fracture community. And this is a case related to mining engineering. This is work done with some collaborators in Chile. They're interested in what happens when you inject multiple cracks at the same time. You can see how those cracks grow, how the fluid evolves, and how they eventually start, some of them interacting with each other. And again, hydraulic fractures, of course, of interest to many applications and sectors. That takes me to the second part, which is kind of a second application, which is kind of a hydraulic fracture problem as well, because it's ice sheet fracture. And the reason we're interested in glaciology is that understanding how icebergs form, how ice sheets fracture, is key to quantifying sea level rise. So the fracture of ice sheets, like you see here, is the main contributor to sea level rise. And there's a lot of discussion in the glaciology community about what would the sea level rise in the next 100 years. Some people say it's 0.5 meter, some people say it's 8 meters. And a lot of this discussion is related to the fact that we don't fully understand very well how this fracture process work. So the ice sheet models that are there, like the ones NASA use, they don't really have a very physical description of fracture of icebergs, fracture of ice. And the reason why they don't have it is because it's a very complicated problem, particularly when it comes to the large scales involved, right? You can see here, this is a scale of 10 kilometers. This is a scale of 10 kilometers, so very large fracture processes. But we are keen on bringing physics into this, in trying to simulate these fracture processes. So we started applying this to glaciology. This was done work a few years ago with Ravindra Dudu and my close collaboration at Oxford of Tim Hageman, my close collaborator Tim Hageman. But basically the idea is as follows. So this is the terminology. You have an ice sheet, then you have an ice shelf. And then in these ice shelves, you have what we call crevasses, which are nothing but cracks, basically. That could be either filled with meltwater or empty. And then when you have enough meltwater on these crevasses, they'll propagate. These are the crevasses. They'll propagate, and you get this iceberg calving event. And the more climate change, the more temperatures increase, the more meltwater you get on these crevasses, and the more this is likely to happen. Because basically, you'll see later, but it's a competition between the compressive stresses that are coming from the ocean and the tensile stresses from the meltwater that is inside of the crevasse. So this is how a crevasse looks in physical reality. And this is a Nature paper that appeared some years ago, not from my group, a group at Columbia University, where basically they used fracture mechanics and they said, okay, let's map the entire Antarctica and calculate based on the amount of meltwater, what is the stress intensity factor, and based on the toughness of ice, which of these regions are going to become stable. And this is fine to a certain extent, but it overlooks many of the key physics that are coming into this, such as viscosity. For example, there's nothing really related to time here. This is static fracture mechanics. And of course, more complicated problems where you may have interaction between crevasses and so on and so forth. So we try to produce a facial formulation for ice sheet fracture. We change a little bit the facial fracture model. We want for one of those stress-based facial fracture models because we want to be less reliant on the facial length scale because of the large scales involved. You have a poro mechanics description of the problem, basically. You have a situation where you have ice sheets, you have a crack, which may or may not contain water inside. And then you have a description of the constitutive behavior of ice, which is given by Glenn's flow law. It's kind of a viscoelastic, viscoplastic flow law. And then when we do that, basically we simulate problems like this one, where you have ocean, you have the ice sheet, you have a crevasse, and you can see here how the loading situation looks, all right? So you have an ocean that is bringing you some gravity load, that is bringing you some compressive stress state. You see this here. You see the stresses are compressive in the bottom, tensile in the top. But then you have a crack which contains seawater, and this seawater creates a tensile behavior. So it's a competition between the tensile behavior by this meltwater and the ocean pushing back, basically. And so you can do that in facial. You can put some meltwater there. You can see how the crack evolves, and you see that it will stop at some point due to these compressive stresses. So you can plot the depth of the crevasse as a function of the meltwater ratio. So depending on climate change, you'll be moving in this direction. So you can compare different meltwater scenarios, and you see that you get a very good agreement with the analytical linear elastic fracture mechanics solution, which is to be expected because facial is based on fracture mechanics theory. But of course, you need to remember that you are dealing, you need to assume that you have incompressibility because of this, due to this Glenn's flow law. And then you can go look at more complicated problems where you have multiple crevasses growing at the same time. You might look at more complicated, where here you can also compare with some analytical models that people have proposed. You can look at cases where you have not only surface crevasses, but crevasses also at the bottom, what we call floating ice shelves, ground crevasses, and you can see how they interact, how they correlate with each other. I'm going a bit fast, but basically the takeaway that I want to say here is that no matter what is the complexity of your problem, you can handle this. And you can even look at real case studies like this Helheim Glacier, where you know the surface of the glacier, so you know when those crevasses are going to start evolving, and then you can run simulations and see when they will grow. You can see here the complete failure of the crevice. And again, I'm showing you 2D examples, but of course 3D comes for free when it comes to phase field, so we can also understand 3D phenomena, what happens with those crevices, how they grow first vertically and then horizontally. And last but not least, the last thing I will say about this ice sheet problem with phase field is that a lot of the discussion in the glaciology community are related to catastrophic events that may or may not happen. They have happened historically, but we don't know if they will happen again. And a lot of the discussion is related to historic data, right? We try to understand in the glaciology community whether the conditions of today resemble those where these catastrophic events happened in the past. And one of them is this marine ice cliff instability. And it's probably the most famous one and the one that brings most uncertainties and discrepancies when it comes to predicting sea level rise. The argument is that in the past, it happens that if your ice sheets are sufficiently tall, the height is sufficiently large, then you get some sort of runaway mechanism where ice sheets start failing by themselves. So you fail first, and then you are again in front of a very tall ice sheet. So again, it will fail again due to its own weight, and then it will fail again and again and again and again, and that will bring significant sea level rise. But again, we don't know if this will happen or not. There's a lot of speculation, but one can use these facial methods to bring a mechanics perspective into this. What does mechanics say about this thing happening or not? And there's a lot of work that we're going on this front, some of it ongoing, but we try to understand, for example, what are the right boundary conditions. We try to see whether this will happen. We try to play with the height and see whether this marine ice cliff instability will happen, whether the cracks will eventually grow. And then we can see what is the height at which this mechanism will be triggered. And then we can compare that to observations and try to understand whether this will not or not happen. And yeah, this is basically the main takeaway. You can bring the physics into glaciology by building on the potential that bigger computers and facial methods give you. Another interesting area is smart materials. In particular, we're interested in shape memory alloys. This is work done by Marlene Simons at Cambridge some years ago. Hopefully, you're all familiar with shape memory alloys. They are quite funny and interesting materials. Let me run that video again. They are materials that can recover their shape by the application of a load or temperature, some sort of external stimulus. It could be load or temperature due to a phase transformation. So as you can see in these funny videos here, you can go from a clip, you can deform your clip, and then you apply a temperature, and because your material has memory, it recovers its original shape. You see this here, a classic spring. You again apply temperature and recover the original shape. So you can apply a load, deform your clip, but then you can apply a temperature and you go back to the original shape. So these are quite funny materials, and the reason why this is happening is because of a phase change from austenite to martensite. So you can see here that brings them two interesting phenomena. One is called the shape memory effect, which you just observed. The other one is the superelasticity. They can go to very high elastic strains and recover their original shape. You see this here. So you start with the stress strain curve. You start achieving this transformation. So this is 0.2. You start going from austenite to martensite. You get non-linear behavior. But then when you unload, you recover it back again from martensite to austenite, and therefore you go back to your original shape. So you can get very, very large strains that are elastic, not plastic. And then the other effect is this shape memory effect, where you again can recover the original shape by changing the temperature. You go from austenite to martensite and the other way around by playing with temperature. But what this means in fracture mechanics is that because you change phase when you increase your stresses, you're going to have three regions. You're going to have an austenite region far away from the crack. As you start approaching the crack tip and your stresses are large enough, you move in here. You go from austenite to a transformation zone and eventually to a martensite zone. So you get these three regions. So what we did was to develop the first formulation of phase field for fracture and fatigue in shape memory alloys. And that allows you to capture the main features that you see. So one of the main features that you see is that you get toughening due to this phase transformation. It's a little bit like plasticity in a way. So if we go back to that classic benchmark that I showed you before of the square plate and the crack, you can see that the force displacement curve goes up, but then instead of dropping sharply, you still sustain some load, you get stable crack growth due to these phase transformations. In a way, it's a little bit like plasticity. And one application that we were very interested in is biomedical stents. So these materials are widely used by the medical community because when you have a stent, basically what you want is you have a cloth, you have something blocking blood fluid flow. So you want to again enable the blood to go along your body, along your veins. And the way to do that is to bring one of those stents, and then you need something that can change shape quite significantly without deforming irreversibly. So this superelasticity capabilities of this nitinol and oil member alloys are very convenient because then you basically compress it, you put it into your body, then it expands, and then it will undergo many cycles of compression expansion as your blood, your heart keeps providing blood to your body. So then the main issue, of course, here is fatigue. You want to make sure that you have something that doesn't damage due to fatigue because it'll undergo many, many cycles in your body. And again, this is work that I did with magnesium oils when I was at Cambridge at Imperial. And you can see here how those stents are growing and how you're getting different behavior and failure due to the number of cycles. So you can use these models to calculate the real behavior of pure biomedical devices. Okay, that takes me to battery materials. We're almost there. This is a very interesting application. Hopefully you all know how batteries work. You all have batteries, I'm sure, in your laptops, in your phones. And the way these lithium-ion batteries work is that every time you see it here in the schematic, but every time you charge your battery, you have lithium ions going from the cathode to the anode. And every time you discharge your battery, you have lithium ions going from the anode to the cathode. And what happens is that every time you charge and discharge your battery, these lithium ions, they are embedded into these anode and cathode particles. So these are typically ceramic materials, and you get this lithiation process where these lithium ions go from here, they accumulate in these particles here, and then when you charge your battery, they leave from here and they go the way, and then electrons go the other way around. And the problem is that every time you do this thing, you're basically swelling and shrinking these particles. These particles, you input a lot of lithium ions there, they change in shape, they swell and shrink. And when you swell and shrink those particles, you get cracks. And those cracks are the main reason why we need to change our phones or our laptops every couple of years, because we are full of cracks everywhere. So we decided, okay, can we do the same as before? And as usual, our approach to all of these problems has always been the same. We want to develop computational tools that allows us to predict when things will fail, or in other words, map safe regimes of operation. If we know when railway infrastructure, when isobursts, when batteries are going to fail, we can tell engineers under what conditions they can operate safely. And the other approach is that we want to build these computational techniques or tools to be able to find solutions to these problems, to test quickly ideas. So we want to, in the case of batteries, we may want to try to put solutions. You may think of putting a coating. And so we want to be able to have a platform that allows engineers to quickly test ideas and to come up with solutions. So again, we said, okay, we are working with multi-physics problems. We have this phase field model that allows us to predict cracks, so why not apply it to batteries? And the models are simple, relatively simple. So again, you solve a displacement problem and a damage problem. But now, in addition, you solve a lithium transfer problem. So this is an extension of Fick's law, where you can see it's strongly coupled with mechanics. So you solve for the concentration of lithium ions in time. And this depends on the hydrostatic stresses. And this also brings some chemical strains. This is this lithiation process. You intercalate lithium there, and that change in concentration brings some chemical strains that rely on this parts and molar volume. And those chemical strains are what bringing the cracks. We're not applying load to the lithium-ion batteries. We're not applying, typically you don't apply a mechanical load. Your phone is standing there. No one is applying any sort of mechanical load. But every time I charge and discharge my phone, this is changing in this, those particles are changing in size, they're swelling and shrinking, and then we get particles in there. And a few people have already looked into this problem with phase field fracture methods, but all of them were simulating only 1/2 cycle. But this is, of course, a cyclic process. So we developed the first phase field fatigue model for this. where again we have a fatigue degradation function. And this was done work by my postdoc Wei Long Ai well, it was a postdoc of Billy Wu at Imperial, who's now an academic in China. And basically we look not only at idealized particles, but also realistic particles that we took from XCT scans. And then we could simulate hundreds of loading cycles, which is relevant for electric vehicles, for example, or phones. And they were able to predict, as a function of the seed rate, as a function of the charge and discharge cycles, what is the propagation of those cracks. And you see some examples here of those cracks growing in idealized particles and realistic particles. And you can see that we can predict, we can vary anything we want. We can change the seed rate and see what are operation conditions that are safe. We can also change the particle size, for example, and tell industry, what is the ideal particle size they should be looking into to prevent those cracks from forming. And not only we can do simulations at the particle level, but we can also do simulations at the electrode level. And this is work done with Adam Boyce from now University College Dublin, back there UCL, and the group of Paul Sharing here at Oxford. And basically they're very good at imaging techniques. So they can produce nice images with XCT scans at the electrode level. We can go from the XCT scan to a finite element model. We can, segment that XCT scan into the finite elements. So we can not only model those particles, but we can see how particles interact with each other and what is the role of other phases that come here, like carbon binders, pores, and other secondary phases. You see an example here. This is what you get from the XCT image. This is what you put in your finite element model. And finally, you run your simulations. And we can do that in 2D and 3D. And you can see how those cracks start to evolve. We can learn things about the heterogeneous electrochemical nature of this process. We can understand, for example, what happens if you reduce the size, the thickness of your electrode, and we can see which batteries are more affected. You see here the content of lithium, the facial variable, and the hydrostatic stresses. And not only we can go up the scales, we can also go down the scales. So these people, again, are very good at imaging. So they can image in XCT scans particle cracking at the macro scale. So we can embed those particles with multiple cracks, and we can understand a lot of these particles crack at the grain boundaries. So we can understand when things will fail at the macro scale level. And that allows us to answer critical questions that the industry is considering. For example, what if you make those particles of single crystals? What if you remove your grain boundaries? Or what if you make graded particles where the grain boundaries are bigger outside of the particle, smaller inside of the particle? All of those questions can be answered with those models that seem to be able to capture nicely what we see in experiments. Okay, and that takes me to, by the way, I should say before I leave them, I didn't have time to discuss the application of phase field models to non-cracking problems, but I also done quite a lot of work with Tongji, with Professor Yin Zhao, on working with phase field models for batteries, not on fracture problems. We're looking at using phase field to describing voiding in all solid-state batteries, which are the next big breakthrough in battery technology, because all solid-state batteries will allow you to increase capacity by an order of magnitude. So a lot of attention is being played there. And again, collaboration work between Tongji and Oxford led to a new phase field model for the evolution of solid-state or voids in all solid-state batteries that is now being considered by industry and others. So I think it's, again, a good example of collaboration. I didn't want to spend too much time on that because I'm talking about fracture purely, but yeah, I'm happy to discuss those details in the Q&A session if you're interested in. And almost there, the very last application, or the one before the last, is functionally degradable and carbon fiber reinforced composites. So I've been doing quite a lot of work on composites as well. First, I'll start with functionally degraded material, which is kind of a composite as well. Functionally degraded materials are very interesting because they are very convenient for applications where you have heterogeneous conditions, basically non-uniform surface conditions, but also when you want to prevent stress discontinuities at interfaces. So imagine here you have a metal substrate, a ceramic. You want to avoid this kind of bimaterial interface, so you make things smooth by having a graded interface, a material property that changes in composition progressively between 100% metal to 100% ceramic. This is what you see here. You can go from this composition of 100% progressively to 100% of your other material, basically. And they're very interesting from a fracture perspective because their elastic and fracture properties vary in space. And this means that your fracture is going to be intrinsically mixed mode. Your stress intensity factors are not going to be only K1. Even under conditions where you have purely mode 1 fracture, so a crack in a uniaxial tension sample, you're going to have crack deflection and mixed mode conditions just because the crack is seeing a material gradient in front of them. So these are very interesting for phase field modeling because we don't know where the crack is going to go. So phase field give you that flexibility of predicting where the cracks will go. And you can see some examples here. We proposed the first phase field model for functionally graded materials. You can see some examples here. Because of the mixed mode, you get crack deflection. You can see that the model seems to agree very nicely with experiments. We can calculate this in 2D and 3D. You can see a comparison with other techniques here. You can see, notice that the phase field not only is able to predict nicely what happens, the crack trajectory resembles what happens in other techniques, but because the method can predict crack nucleation as well, we can see that the crack can go all the way to the defects, to the second defect. This is a 3-point bending experiment with these classic holes. It goes to the second hole, but it initiates again, and then goes to the third hole, and then initiates again from the top of the third hole, and you get the complete failure of the sample, which is something that all the methods based on remeshing, XFEN, and so on are unable to predict. We also did quite a lot of work on fiber reinforced composites. And I find this very interesting because not only because we get a good agreement with experiments, you can see this here. Basically here we're using the phase field to simulate the evolution of cracks in the matrix, in the fibers, and the fiber matrix debonding, where we have also done simulations using cohesive sum elements. In fact, what you see here is that example that you're seeing here. We're using the phase field to predict cracking in the matrix and the fibers, and then cohesive sum elements to predict the cohesion, the debonding between the matrix and the fibers. But what I find powerful about this, not only the ability to simulate experiments quite nicely, but is the ability to run 3D simulations. Because when you run 3D simulations, you can capture the fiber bridging phenomena. So you can capture the arc curves, you can capture how, as the crack propagates, the fibers are naturally bridging the crack. And this is very powerful because all the other models that I have seen before, the toughening due to fiber bridging, they provide us an input to the model. So you need to run an experiment, you calibrate that, and you put it into your model. Here, we predict the fiber toughening as an output of the model. So we can try what happens if you change the shape of the fibers, what happens if you change the strength or the toughness of the fibers, and so on and so forth. And lately, we have also extended this to deal with multi-physics environments. So this is work in collaboration with Wei Tan at Queen Mary, University of London. And it's particularly interest to wind energy. There's a lot of cases where we see a lot of degradation due to the environment. Again, we're interested in interdisciplinary civil engineering problems. So there's a big effect of the environment. But what we can see is that we can simulate, those couple of problems similar to the battery problem. You can simulate the transport of humidity, and you can simulate the interplay with mechanics and with fracture, and we can capture what is the behavior of those components. And the last thing I would say about composites is carbon nanotube composites. And I'm very close to finishing my talk, by the way. These are very interesting composites, and we want to use them as kind of a smart skin. So for, I would say, new structural health monitoring techniques to be able to tell us where we have cracks in our civil engineering infrastructure. This is an idea of my former postdoc, Enrique Garcia Macias. And we work with our PhD student, Leonel Quinteros, and what he did here was to try to simulate the effect of carbon nanotube composites. And he did that through 2 classes of models. One where you simulate also the RBEs of the carbon nanotubes, but another one where you homogenize basically these carbon nanotube composites, because carbon nanotubes are, nanoscale. So we don't want to simulate things discretely at the nanoscale. So we have homogenization techniques where we basically capture the effect on the mechanical properties using mean field homogenization, but also on the fracture properties, and how they contribute to preventing crack growth by some sort of fiber toughening effect, but also where you have phenomena such as carbon nanotube pull-out or aggregation of those carbon nanotube composites. So again, all captured through this toughness and through homogenization. And just to show you some examples, we can capture, you can come up then with some effective mechanical and fracture properties that you can easily incorporate into your phase field model, and then you can capture the different degradation mechanisms. You can capture how cracks evolve and how you can increase the toughening as a function of the characteristics of those carbon nanotubes and how many carbon nanotubes you have in there. And we have combined this with electromechanical modeling because we want to use those carbon nanotubes to tell us something about a structure. So we want to be able to capture what happens when cracks evolve in our structure, how we will be able to see this in terms of the electrical field. So we can come up with a multi-physics model where we degrade the stiffness and the electrical conductivity, and we can compare that to experiments. You can see the phase field and the electric potential. So now we know a crack has propagated. There's this discontinuity in the electric potential, and we can do that in many different problems, different crack orientations, and even in 3D components where you may have multiple defects, and eventually you get this kind of piezo-resistive electromechanical behavior. Okay, and last but not least, my last application will be related to reinforced concrete. In particular, we're very interested in corrosion-induced cracking of reinforced concrete. This work led by my student Eugen Korek led to a number of papers. The first one was published in Construction and Building Material, but there's another one in Cement and Concrete Research that I think you'll find interesting. Eugen just finished a year ago his PhD in my group and was awarded the prize to the best thesis in computational mechanics in the UK. Now he's competing for the one in Europe, awarded by ECOMAS. And basically the idea behind his thesis was to use this facial phenomena with this kind of multi-physics modeling approach to resolve the physics underlying concrete cracking, or cracking in concrete reinforced structures. So concrete structures have been reinforced with metallic rebars, of course. And when you do that, basically, the beauty of it is that it allows you to not only predict, the cracking patterns that you see here, but also the cracking patterns that you see in experiments. And by the way, I should emphasize we use Wood's model here, so the phase field Kuznetsov model. But also, it allows you to critically go from laboratory experiments to large-scale phenomena. And this is not only a matter of space scales, but of time scales. We normally do accelerated corrosion tests in our labs. But if we can capture the physics of the problem, we can make sure that the model agrees with accelerated corrosion tests, and then take that model to simulate the scenarios of natural corrosion. So then predict what's going to happen in civil engineering infrastructure over decades. And the last thing I'll say about this is work done with Carmen Andrade in Spain. We've also been doing a little bit of work on corrosion and electrochemistry to, again, forget about, I would say, accelerated experiments. Try to understand what happens when you do natural corrosion, when you simulate what's happening in a bridge over decades. And again, this is the goal of using models to go from these accelerated experiments that don't seem to be that useful in predicting what's going to happen in civil engineering infrastructure over large periods, and then taking them to large-scale structures. So let me just conclude to give some time for questions. It's been almost 50 minutes of talking, so I'm sure it's been a lot of information thrown at you, and I appreciate your patience. But let me just say the key takeaways of this talk. So I think the key takeaway is this facial modeling has really revolutionized the modeling of fracture mechanics. I consider myself to be a computational fracture mechanics person. I've worked with XFEM, with remeshing, with Kuznetsov models, and I've never seen anything like this. I'm not the main developer of facial fracture. I didn't come with it. I came to it years later, but I do like it very much. So I have embraced it fully, and I think it's going to be a big revolution in fracture mechanics. We have shown that you can, capture any arbitrary complex problem, 2D, 3D, no matter if you have crack bunching, crack coalescence. We have tried to contribute to this community. We have tried to do so by providing new solution schemes that I believe can make significant progress in capturing cracking process efficiently and robustness. We've also shown that facial methods are not only computationally robust, but they also deliver a very good agreement with experiments, with conventional fracture mechanics theory. So it's a method that is physically sound. And we have tried to contribute to this so-called facial revolution by coming up with new facial fracture formulations in multiple areas, including shear memory alloys, functionally gray materials, fiber reinforced composites, ice sheets and glaciers, areas that I'll discuss next week, like hydrogen exposed materials, but also rocks and rock-like materials, hydraulic fracture, reinforced concrete structures, and battery materials. So we've tried to contribute to this community by proposing new formulations and taking the application of these methods to engineering problems across disciplines. Last but not least, I will just thank you, of course, all of you, for your very kind attention over what is a lot of slides and a lot of content. I tried to go slow and try to emphasize the key points. Hopefully, you've been able to follow nicely. But the one last thing that I'll say is that, of course, that I want to emphasize is that all the codes that we develop are openly shared. So all of the results that we develop codes for Abacus user subroutines, very simple user subroutines using user material subroutines like UMATs, Console, which now has facial inbuilt, but we also develop codes for ourselves in MATLAB, C++ that you can download, in Julia. We also contribute to open source projects, Moose, Phoenix. So all the results that I showed you today, you can go to my website, you can download the codes, and you can reproduce your results at home. And if you have any questions, feel free to reach out. I'll be happy to help with any issues that you may have with the codes. That's all. Thank you so much for your patience. And yeah, again, excited to, as usual, to engage with Tongji engineers. Thank you.
Thank you so much, Emilio. It's really, really very wonderful, beautiful. So
Thank you.
I think the lecture includes the principles of phase field, applications on fatigue, hydraulic fracture, ice sheet fracture, shape memory alloys, multi-physical phase field, like application to bacteria, and also the functionally graded materials, fiber reinforced materials, CNT-based composites and reinforced concrete. It's really very rich and with the very beautiful results and also the ideas embedded. I think now we have some. We have several minutes for some questions. Is there any question from the audience? Yes, please. I think you can just open your. Oh, is there any questions? I think you can unmute yourself now if you have any questions, or otherwise you can also post questions in the chatting box if you want. It's also fine. Yes.
Okay, Professor, I have some questions. Okay, thank you.
Sure.
Thank you very much. Thank you for excellent and detailed presentation. And your presentation includes several interesting topics, and I have 3 questions. And my first question is that the concrete is a typical heterogeneous material. And have you ever tried? Have you ever considered the randomness of concrete, such as generating the random field of the properties of concrete, such as just modulus and the stress of the concrete?
Yeah, it's a very good question. Thank you for your question. In fact, I have a student, Lorenzo Ciavarini, who is working on concrete, and he always says concrete is the most difficult material because of the different heterogeneities at the different scales. So indeed, it's a problem. There's various ways you can try to bring that heterogeneity. So some of the work that Lorenzo is doing is looking at the RBE scale, where you may have different chemistries. This is particularly useful for low carbon cements. So the industry wants to come up with new low carbon cements. So they want to make sure that the new chemistries that they come along are able to have, compressive strengths that are good enough for structural application. So we try to accelerate this process by running sort of RBE type of simulations. We haven't published much on that front, but it's coming soon. The other approach is what you say, right? At the macroscopic scale, we can randomize properties to try to, for example, I have a visitor now, Mario from the University of Girona. We're working on a paper where he's looking at basically cracking patterns in concrete. And you can see that often you can only capture the cracking patterns that you see in the lab by accounting for that heterogeneity. And you can do that in multiple ways. You can vary, for example, the strength of the material. You can do that following a Weibull distribution, but it's exactly your point. You can easily incorporate in these models, you can easily vary properties in space. So if you know more or less how your strength will change in space, you can embed that into the model if you want to do macroscopic simulations. Yeah.
Yeah, I see. Thank you for that. Okay, my second question is that in fractional mechanics, as we all know, the size of spaceman is infinite, so the fraction energy is a constant. But in actual engineering, the fraction energy is measured in the spacemans of limited size. So the fraction energy depends on the geometry of the spaceman, such as the length of the initial notch and the type of the spaceman. However, as we all know, the fraction energy is still taken as a constant in most of current field simulation. What do you think about this? Yeah.
Yeah, it's a good point. Thanks for this. So I guess it depends who you ask. If you ask people like, I don't know, Bazin, for example, he will talk about size effects and things like this.
Yeah.
In theory, so if your sample is big enough, a fracture energy or toughness being a material property should be not dependent on, should
Yeah.
be a material property, right? It could not depend on how you load your sample. It shouldn't be depending on the size of your sample. We do know that in order, of course, to get this this condition, we need a valid K field. So we need to be able to have a sample that is big enough. And that is easier done than said in some materials than others. But in principle, we do, in most of the cases, most of the materials we work, we do have fracture toughness measurements over samples that give you a valid fracture toughness estimate. And if you give you a valid fracture toughness estimate, then that is a material property that you can carry on as a constant. Yeah.
I see. Thank you. On the
So you will capture with the phase field, and there's a very nice paper by Lalit Anand from MIT showing with a similar model like these facial models that you can capture those size effects. So you could input that constant material property, but see different sort of fracture behavior as you change the shape of your material, because you naturally capture how the fracture processor interacts with the geometry.
Yeah, I see. Thank you, Professor. And the last question is that I noticed that you have tried the BFGS algorithm in your simulation. So have you ever met the convergence problem, such as, in other words, how to ensure that the value of the phase variable is between 0 and 1? And this is not my research topics, but some other scholars have raised the same question, and I want to know that and how it should be. Okay.
Thank you. Yeah. So we. Well, the group of Wu in China has also championed this method. We have championed this BFGS approach. It doesn't change, so the problem is well bounded, so phase field never really evolves beyond 1. Sometimes people show small changes, but I think this is more post-processing extrapolation. So the problem works quite well. What I would say is that convergence is quite good and is quite improved. However, both the approach that Wu used and we used is the same. So in a way, there's a lot of BFGS methods, so to say, or there's a lot of versions of the BFGS method. So if you want to make it work fine, you need to have everything that we take into account, which includes some line search. And this is the particular Abacus implementation of BFGS. I've been contacted by other groups who try to implement this in their own codes, and they only manage to get it to work very nicely once they combine it with the line search and they use the specific BFGS implementation that Abacus has that makes the matrix positive definite.
Yeah, I see. Thank you. Thank you, Professor. Thank you for
your interesting questions.
Yeah.
Thank you.
Thank you very much. I think because the limitation of time is around 1.5, Professor Emilio Martinez-Paneda really gave us a very long time, very excellent, but long time, I'm afraid you are a little bit tired. So
no, it's okay. Oh, yeah, my pleasure. I mean, we do have another talk scheduled in November. So of course, if anyone wants to carry questions from here or there, I'm happy to answer them as well.
Yes, that's great. So I think that as Emilio mentioned, that the next lecture will be in the evening of November 19th, I think, from 20 p.m. In Beijing time. And then I think this is all for today. Also, thank you all very much for your kind attention, and welcome also to the next one. So thank you very much again, Professor Emilio Martinez-Paneda. Looking forward to see you next time. Thank you very much.
Thank you very much, Professor Chen. Thank you all.
Great.
And looking forward to seeing you again. Thank you.
That's great. See you. Bye-bye.
Thanks. Bye-bye.
Bye-bye.